Hey guys, welcome back to another video. In today's video, I'm going to be discussing the concavity of functions and the second derivative test. So let's begin. So let's start with concavity. The definition is that concavity describes the curvature of a function. So if you see like a function like this, you would say that it's concave up because it curves upward. So let's start with this. If f of x is differentiable on an open interval, then f of x is concave upward on the interval if f prime of x is increasing. F of x is concave downward on the interval if f prime of x is decreasing. So to illustrate this, let's start f of x right here, and as we go up, the slope gets steeper and steeper, which means that derivative is increasing, which would mean that it is concave up. But if you start from here and you start to go down, and the slope starts increasing and increasing, that means they're concave downward. So in a graphical meaning, concave up means if f of x is concave up on an open interval, then the graph of f of x lies above all of its tangent lines in that interval. So say we have the graph of x squared, and its tangent lines go like this. As you can see here, its tangent lines will lie below it if it's concave up, and if f of x is concave down at an open interval, then the graph of f of x lies below all of its tangent lines in that interval. So just get negative x squared. So its tangent lines will go like this, and the graph will lie below all of them, which means that it is concave down. The second derivative can be used to test for concavity. So the second derivative is the rate of change of the derivative of f of x, or the rate of change of the rate of change of the original function. So if the second derivative is greater than 0 on an open interval, then the graph is concave upward. So that means that the derivative for some function is increasing, or that the slope of the function is increasing. And if the second derivative is less than 0 on an open interval, then the graph is concave downward, or that the derivative is decreasing, which means that the slope is getting steeper, but in the negative direction. So to test this out, we first solve for the second derivative of x, and then we solve for where the second derivative is equal to 0 or undefined, and then we use these x values where it's 0 or undefined to split the domain into test intervals, and then we check the sign of the second derivative in each open interval. So let's have this example where f of x is equal to sine x plus cosine x. We're going to find the open interval of the graph where the function is concave upward or downward. So let's find the first derivative. The first derivative will be equal to cosine x minus sine x, and the second derivative will be equal to negative sine x negative cosine x. So now we're going to split the domain into intervals where the second derivative is equal to 0 or undefined, so that we can find on which interval is concave upward or downward. So now we have 0 is equal to sine c minus cosine c, and if we were to move cosine c to the other side, we get that sine c is equal to negative cosine c, because this turns positive when I move it to 0, but since it's a negative, it becomes negative again. So now we're going to look for values of c where the sine is just a negative of the cosine from 0 to 2 pi. So this occurs from this angle and this angle over here. This is going to be 3 pi over 4 and 7 pi over 4, because over here sine is positive but cosine is negative, and over here cosine is positive but sine is negative. So our intervals are going to be from 0 to 3 pi over 4 to 7 pi over 4 to 2 pi. And we're going to plug in values in between these intervals to see the sign of the second derivative. So let's plug in pi over 2 into here. So negative sine pi over 2, sine pi over 2 is 1, so we're going to get negative 1. Cosine pi over 2 is 0, so we're going to be left with negative 1, which is less than 0, which means that this is negative. So the second derivative is negative here, which means that the graph is concave down from 0 to 3 pi over 4. So from this interval, it's concave down. So now let's test the second interval. And we can see that pi is in between these two intervals on the unit circle. So we're going to plug in this pi. So sine pi is 0, and cosine pi is -1. But -1 times -1 from the negative over here gives you +1. And 1 is greater than 0, which means that f of x is concave up from 3 pi over 4 to 7 pi over 4. Because from this interval, the second derivative is positive, which means that the graph is concave upward from this interval. So now we're going to test out the last interval. So I'm going to put 11 pi over 6, because that's just right before 2 pi, and it's bigger than 7 pi over 4. So plugging in 11 pi over 6, negative sine 11 pi over 6 will be -1 multiplied by -1/2, which makes this positive. So now we have 1/2, but now we have to do the same thing for cosine. Negative cosine 11 pi over 6, or 1/2 minus square root of 3 over 2. If we were to combine these into one fraction, we get 1 minus square root of 3. Square root of 3 is bigger than 1. So this is going to be less than 0, which means that this interval is negative, which means that the graph is concave down from 7 pi over 4 to 2 pi. Okay, so now let's talk about points of inflection. The definition of a point of inflection is that a point of inflection is a point where the graph of f of x changes concavity from concave upward to concave downward, or from concave downward to concave upward. So it would look something like this. So this part of the curve is facing up, but this part of the curve is facing down. So the point of inflection will be somewhere around here, because the concavity over here is facing up, but now it's facing down. So possible points of inflection can occur at the values of x where the second derivative is equal to 0, or the second derivative does not exist. The reason why I put possible is because the second derivative equaling 0 or undefined does not guarantee a point of inflection. So in a similar process to extrema, each possible point must be tested on the second derivative with nearby values to ensure that the concavity changes at that point. So we have some interval from a to b, and we find a c where the second derivative is equal to 0. We have to test the values around it to make sure that the sign of the second derivative changes, or that the concavity changes. So if we were to change from negative to positive, that means that x equals c will be a point of inflection because the concavity changes from negative to positive, or from positive to negative. So if the point c, f of c, is a point of inflection on the graph of f of x, then the second derivative at c is equal to 0, or the second derivative at c does not exist. So this is how to find points of inflection. So first we find the second derivative of x, and then we solve for when the second derivative is equal to 0, and when the second derivative does not exist. So these will be our potential points of inflection. And then we're going to test intervals around every potential point. So we're going to choose values slightly smaller and larger than each possible x value. And then we're going to determine the signs of the second derivative of x on each interval. So the second derivative of x is greater than 0, that means it's concave upward. And the second derivative of x is less than 0, that means it's concave downward. So we're going to use this to confirm if the concavity changes. A point of inflection occurs if and only if concavity changes from either upward to downward or from downward to upward. And then we write down the coordinate of the inflection point. So this is a summary table for function behavior based on the first and second derivatives. So basically these are the derivatives, the first derivative and the second derivative. And then you test if the first derivative is greater than 0, that means that the function is increasing. If it's less than 0, that means it's decreasing. If the second derivative is greater than 0, that means that it's concave upward and that it curves upward. And if it's less than 0, that means it concaves down and that it curves downward. So this example asks us to find the points of inflection for the function f of x is equal to x cubed minus 6x squared plus 7. So we're going to start off by finding the first derivative. So this would be 3x squared minus 12x. And then after that, we're going to find the second derivative. So now we have 6x minus 12. And now we're going to find when the second derivative is equal to 0. So 6c minus 12 is equal to 0. I'm going to add 12 to both sides. And now we have that c is equal to 2. So now we're going to test the interval around it. Since the second derivative is a polynomial, it goes on from negative to positive infinity. So now we're going to test out the value of 2. So from the left, the second derivative, so let's plug in 6 of 1 minus 12, and that would be negative. So over here is going to be negative, and let's plug in 3 for x, so 6 times 3 minus 12 will be equal to 6, which is greater than 0, which yeah, this is positive. And since the concavity changes at 2, that means that the point 2, f of 2, is the point of inflection. So let's solve for what f of 2 is. F of 2 would be 2 cubed minus 6 times 4 minus 24 plus 7. So this would be negative 16 plus 7. So now we have that this is equal to negative 9. And that's going to be our point of inflection for this graph. Okay, so now let's talk about the second derivative test. Suppose that f of x is a continuous function for first and second derivative. Let c be a critical number where f prime of c is equal to 0. If the second derivative of c is greater than 0, then the graph is concave upward, and there's a relative minimum at x equals c. If the second derivative at c is less than 0, then the graph is concave downward, and there's a relative maximum at x equals c. If the second derivative is equal to 0, then the test fails, and you use the first derivative test. So the second derivative test is useful when finding the second derivative is easier than testing values around the first derivative or the first derivative test, and it provides a quicker way to classify critical points as relative minima or maxima only if the second derivative is not equal to 0. The second derivative test does not work when f prime at c is undefined. Okay guys, so this is going to be the end of the lesson for concavity and the second derivative test. I hope you enjoyed watching today's video, and stay tuned for part 2.